All right, today we're going to be talking about relations and functions as well as domain and range. So some definitions that are going to be really important because you are definitely going to be asked questions that relate to these definitions. So if you're a flashcard person, you might want to do some flashcards for relation, function, domain, and range. Because I think that those will help you. All right, so a relation is information that can be represented by a set of ordered pairs. Now, the key word here is can be represented by a set of ordered pairs. It doesn't mean it's always given to you in that format. So you probably already know that ordered pairs come in the form x comma y. X is considered your input variable, Y is considered your output variable. So any type of information that can have an input and output set is going to be a relation. So here is an example of a relation given to us in ordered pair format. Once we have a set of ordered pairs, there are lots of different ways that we can represent it. So one way is with a table. And again, each of these ordered pairs, the first coordinate is your x, the second coordinate is your y, and the way that you match them up matters. So this first x is paired with this first y, so they go right in the same row of that table. Then I have 2, 3, so 2 is the x, 3 is the y, 3, 4, 4, 3, and 1, 5. And so all you do is just take each ordered pair and write it in its own row. So for a table, each ordered pair gets a row. And that's how we turn it from a set of ordered pairs into a table. Another way that we can represent a relation is with what's called a mapping. And in a mapping, we have two usually ovals that we list. In the first oval are inputs. And in our second oval, we list the outputs. So all of our inputs are our x's. So I have 1, 2, 3, 4, 1 again. I don't need to list it twice. You only list each value one time that appears. So 1, 2, 3, and 4 are the only separate inputs that I have. The outputs that I have, 4, 3, 4, 3, and 5. So 3, 4, and 5 are the outputs. And then the reason it's called a mapping is because we show with arrows which inputs are associated with which outputs. So I'm actually going to look at the table here because it's a little bit easier to look at than the set of ordered pairs. So for input 1, I need to draw an arrow to output 4. So use a different color here to make it stand out. So input 1, output 4. Then I have input 2, output 3. So I draw arrows that way. The arrow always starts with the input and goes to the output. Then I have input 3, output 4. There we go. Then input 4, output 3. Up here. And then finally, input 1, output 5. And so the arrows show us that association. Another way that we can represent a relation is with a graph. And so that's just simply plotting ordered pairs like you've been doing for years. Remember that this is your X or your input axis. This is your Y or your output axis. So use the table or the set of ordered pairs. Input 1, output 4. So write 1, up 4. Then 2, 3. So 2, 3 would go right here. Then I have 3, 4. So 3 up to 4. Then 4, 3. And then 1, 5. Go right there. Now, a function. This is our second important definition. A function is a relation, but it's a specific type of relation in which each input has exactly one output, meaning that every input that you have, each X is assigned to exactly one Y. So each X assigned to exactly one Y. So for example 2, we want to decide, is the previous relation a function? So we're going to look at our ordered pairs, and do I have each X assigned to exactly one Y? So I look at each X. 1 goes to 4, 2 goes to 3, 3 goes to 4, 4 goes to 3, and then 1 goes to 5. These 1 inputs are assigned to 2 different outputs. So we would say no, it is not a function. Input 1 has 2 outputs. In this case, the 2 outputs were 4 and 5. So in the list of ordered pairs, we just identified if there was an X that had more than one Y. So how do we know based on the table? If repeated X values have different Y's, then it's not a function. Based on the mapping, we can tell by if an input has 2 different arrows. Because here, inputs 2, 3, and 4, there's nothing wrong with them. They're all going to just one place. But input 1 is going to both 4 and 5 in the output table. How do we know based on the graph? On the graph, we know if a plotted point has another point directly above or below it. So if you look here, these 2 points are directly above and below each other. None of the others are, so it's these 2 together that cause the problem. Which leads us to our next important piece of information, which is the vertical line test. sometimes all you're given is the graph. So if all I had was this graph and I knew plotted points would give me, if they lined up directly above and below, that wouldn't be a function. But sometimes we don't have plotted points. And so we have to look at an actual picture. And so that's when we use the vertical line test. You can determine if a graph is a function if you draw any vertical line. Vertical lines go up and down, remember. It's only allowed to hit one point and still be a function. If you can draw a vertical line that hits 2 points or 3 points or 4 points or anything more than 2, then that relation is not a function. So if we want to look here, I apparently didn't finish typing this, but I wanted to say which of these graphs are functions. So if I draw a vertical line on this first graph, boop, very first vertical line that I draw hits 2 points. So this is not a function because the vertical line that I drew hits in 2 or more points. And it's not just one vertical line. You have to think of all the vertical lines that you could draw. So here I draw one, it only hits once. But I don't stop there. I should keep imagining that I'm keeping on drawing, but none of those, nothing I could draw is going to hit more than once. So this is yes, it's a function. Vertical line, these are all good. So this one's tricky because right here, it almost looks like it fails. But the trick is that these are open circles. Those aren't actually ordered pairs, right? Because we learned when we did inequalities that open circles meant we weren't including that. So this would be yes, it is a function. So now, in this space on your notes, I want you to go ahead and draw your own function. So you can draw anything you want here, but make sure it passes the vertical line test so that it could become a function. All right, example 4. Which of the mappings or functions support your answer? So again, mappings. How do we know based on a mapping? If an input has 2 different arrows. So look at our inputs and look to see if any one input has 2 different arrows. So what I want you to do, we're going to call this guy A, B, and C. I want you to tell me which of these A, B, C are functions. So go ahead and pause and answer that question. Okay, so this one, this input only has 1 arrow, 1 arrow, 1 arrow. So this is a yes. And we say this is our support. Each input has exactly 1 output. We use these same phrases every single time. So when you're asked to support your answer, if it's a yes, you say exactly this. Each input has exactly 1 output. On B, input 5 has 2 arrows. So this is a no. And we say input 5 has multiple outputs. You can say how many. In this case, 2 outputs. And what are those outputs? 6 and 10. Last one. C, each input only has 1 arrow. So this is a yes. And we say the exact same thing we did in A. Each input has exactly one output. Okay, so these two phrases you need to learn. Make sure you can word for word state these, because that's what you're going to need to be able to do when we get to the Unit 2 test. Also, this typically shows up on the end of course state exam as well. All right, example 5, is the relation a function? So A, B, C. Again, I want you to go ahead, pause it, answer this question. Is A function, B a function, C a function? So go ahead and choose of your A, B, and C, and then unpause to check. All right, in A, my inputs are 1, 3, 5. Each of those inputs has exactly one output. So yes, and that's exactly what we say. Each input has exactly one output. Then I look at B. 1, 2, 3 for my inputs. So I'm good. Yes. Each input has exactly one output. Finally, C. 1, 1, 1. Ooh. Inputs repeated with different outputs. So this one is a no. Input 1 has 3 outputs, 2, 3, and 4. So not a function. All right, next definition. So you should have relation, function as your definition. Now we're adding domain. The domain of a relation is the set of all input values. Our inputs are typically the x values. So for the examples above, we're going to list the domain. So domain are our inputs. In this case, I have 1, 3, 5. When you list domain and range, you don't list things more than once. So if you have a repeat, you only list it one time. For B, my inputs, my x's were 1, 2, and 3. And for C, 1, 1, 1, like I said, you don't list it double. Don't repeat it. It's just one. That's the domain, and that's it. The range of a relation is the set of all output values. Our outputs are usually our y values. So if I go to A, y values 2, 4, 6. In B, 2, 2, 2. Don't repeat it. It's just 2 is the range, and that's it. For C, my range 2, 3, 4. And we've got our list. So the phrase you want to remember, just like we use PEMDAS to remember order of operations, we want to remember Dix-Roy. And that stands for domain input x values. So DIX, domain input x values. Roy, range output y values. So that's what we want to remember is Dix-Roy, so you know which is which. All right, very last thing we're going to do here is we're going to use an equation to represent a relation or function as well. So we have this equation, y equals 3x minus 4, and we want to create the various representations of a relation. So in a table, sometimes they'll tell you what values to use. In this case, we're just going to do, let's do 1 and 3 and 5. So we're going to use 1, 3, and 5 for our inputs in our table. To get the outputs or the y values, we have to plug in these x values. So y equals 3 times 1 minus 4, because all I'm doing is plugging in 1. 3 times 1 is 3, minus 4 is -1. So that's the y that we put in the table. Then I'm going to plug in 3. So 3 times 3 minus 4. 3 times 3 is 9, minus 4 is 5. And then finally plug in 5. 3 times 5 minus 4. 15 minus 4 would give me 11. So this would be my table. When I create a mapping, I draw my 2 ovals. I've got 1, 3, and 5 here. -1, 5, 11 here. List of ordered pairs. 1, -1, 3, 5, 5, 11. And normally we put ordered pairs in the little braces. And then for the graph, we just plot those. 1, -1 would be down here. 3, 5. And 5, 11. Be one little spot above where it ends there. Okay. That about wraps us up for our 5152 lesson. Make sure that you reach out if you have questions.